Hey everyone, and welcome to RUBIN'S Mind Lab, where we break down the latest research into what it really means. Ever wonder why sometimes you can do something perfectly, then totally mess it up the next time, even though nothing seems to have changed? Well, today we're diving into some fascinating psychology research that looks at how our bodies and brains learn to control movements, and how easily that control can be messed up. It is all about something researchers are calling stabilizing variables. So imagine your brain is like a super smart director constantly telling your body what to do. But it is not just about sending simple commands. Our brains have to deal with all sorts of messy stuff like delays in getting information, random noise in our senses, and limits on how fast they can process things. This study proposes that for our bodies to move smoothly and learn new special internal tools, called stabilizing variables. Think of these as internal tricks or dynamic states that help the controller, your brain, make corrections on the fly to keep things steady and accurate. The researchers are suggesting that a lot of what we think of as learning or context-specific behavior might actually be about whether these stabilizing variables are available and working well for the controller. It's like having the right tools for the job. If you have the right tool, you can fix things easily. If you don't, even if you know what is wrong, it is much harder. To figure this out, they ran some computer simulations. They created a simple model of a physical system, something like a mass with springs and dampers, which is a common way to model how things move in the real world. Then, they added a controller to the system. They compared two versions, one with a basic controller and another with a controller that had these special stabilizing variables added. In the first set of simulations, they tested how well the controller could handle a constant unexpected force pushing against it, like trying to push a door that's harder to open than usual. The basic controller struggled and ended up way off target. But the controller with the stabilizing variables slowly learned to counteract this force and kept things much more stable. This meant the simulated system tracked the desired movement much better, with about a 70% reduction in error when the stabilizing variable was present. When the unexpected force was removed, the stabilizing variable kind of lingered for a bit, causing a temporary overshoot, like your body remembering the force and overcorrecting for a moment. This after effect is something we see in real life too. Then they tested a different scenario, a temporary increase in damping, which is like a resistance that depends on how fast something is moving. Think of trying to move your arm through thick syrup. Again, the controller with the stabilizing variable, specifically designed to handle this velocity-dependent resistance, performed much better during the movement phase. It reduced the errors during the motion significantly. And just like before, when the resistance went back to normal, the stabilizing variable's lingering effect caused the temporary overshoot. But these were simple one-dimensional systems. To make it more relevant to human movement, they moved on to simulating a two-dimensional reaching task, like moving your arm on a table. They added something called a curl field. This is a force that tries to push your hand sideways, perpendicular to the direction you're moving. It's a classic way to study motor learning because it requires you to adapt your movements. Here, the stabilizing variable they focused on was essentially an estimate of the arm's velocity, which is crucial for countering a velocity-dependent force. Like the curl field, they then played with three key factors: delay, noise, and something called contextual identifiability. First, delay. They introduced a delay in how quickly the controller received the velocity information. Even a small delay, like 0.1 seconds, significantly degraded the controller's ability to counteract the curl field, meaning the paths became much more curved and farther from the intended straight line. As you can see from the numbers, without compensation, the error was quite large. With perfect compensation, it was almost zero. But adding delay or noise, or both, brought that error back up substantially. This shows that for a variable to be stabilizing, it has to be available quickly and reliably. Information that arrives too late or is too fuzzy is just not that useful for real-time control. Next, they looked at contextual identifiability. Imagine you're in a situation where the force field can push you left or right. Your brain needs to figure out which direction it's going to push you, and then use the right compensation. They simulated situations where the context was clear, where it was ambiguous, and even where it was misassigned. When the context was correctly identified, compensation was great and the paths were nearly straight. But if the context was absent, or even worse, misassigned, the compensation didn't help at all and the paths were just as curved as if there were no compensation at all. This is critical. It's not enough for the brain to have the information about velocity. It needs to know which corrective action to apply based on the situation. So, what does all this mean? The researchers argue that for our bodies to learn and perform movements smoothly, especially in challenging situations, we need these stabilizing variables. These aren't just abstract pieces of information. They are internal states that the controller can actually use to make corrections in real time. They suggest that things like lead-in movements, those few small movements you might make before a big one, might be helping to kickstart or tune these stabilizing variables. If these variables decay quickly, it also explains why things like dwell time effects happen. How long you wait between movements can dramatically change how well you perform the next one. It's not necessarily that a whole motor memory is being forgotten, but that the supporting stabilizing variable has decayed. The beauty of this idea is that it connects motor learning to fundamental principles of control systems. It's not just about predicting errors or inferring context. It is about whether the information the brain has access to is actually usable for stable control given biological limitations. Think of it as a control feasibility check. Is the information reliable? Is it fast enough? Can the system actually do something with it? Now, it is important to remember that these are simulations. They use simplified models and didn't get into the nitty-gritty of how the brain discovers or learns these stabilizing variables. That's a huge and complex area for future research, but these simulations are really good at illustrating the control consequences once these variables are available. The core takeaway is that motor learning and performance aren't just about having the right knowledge or prediction. They're fundamentally about having the right internal tools, these stabilizing variables that make precise and flexible movement possible given the messy realities of our biological systems. It suggests that learning failures or inconsistent performance might not just be about forgetting or confusion, but about the temporary or permanent loss of these critical control resources. This research offers a powerful new way to think about why we get better at things, why we sometimes struggle, and how our brains actively manage the complex task of making our bodies move in a predictable and controlled way. It is a reminder that the story of motor control is as much about the how of precise execution as it is about the what of learning and prediction. What do you think about this idea of stabilizing variables? Does it help explain some of your own experiences with learning new skills or adapting to changes? Let us know in the comments below, and if you found this useful, don't forget to like this video and subscribe to RUBIN'S Mind Lab for more deep dives into the fascinating world of psychology and neuroscience. We'll see you in the next one.